Hello everyone. Today is the 36th day of Leetcode 75 challenge. Let's begin with the 36th question. Question 437, path sum 3. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Let's understand the problem in the easiest way possible. So you are just given a root of a binary tree. Fine. Let's draw a random tree here so that we can understand the explanation much more properly. Okay. So now second part, the path in the tree is defined as any sequence of nodes from starting node, okay, let this be the starting node, to any node, let this be the any node, okay, in the tree along the parent-child connections, okay. So this becomes the parent and other nodes after this particular parent node becomes the child node, right? And what they're trying to say is here is they're trying to give the definition of a path in a tree. So if you go from 1 to 2, then 2 to 3, and you stop here, then 1 to 2 and 2 to 3 becomes path of the given tree from the parent node to the child node. Fine. This is what a path is in the binary tree. Fine. In this case, it is only going downwards. Fine. A path is considered valid if the sum of all the node values in that path is equal to the given target sum. So in this question, you are given a value target sum, and that target sum could be 3, 4, anything, right? And you have to find a path whose total value accumulation or whose all value sums up to that particular target. For example, if you had a target of, let's take 1, 2, 3, 3 plus 3, 6, right? If you had a target of 6, fine. So path from 1 to 2, 2 to 3 sums up to be 6, right? So this is our one of the path, fine. So similarly, we have to find your task is to count all such valid paths in the binary tree. So in that case, you have to count, look, if you could see 1 and 5 also sums up to a 6 value, fine. So there are total 2 paths in here in this given tree, fine. This path can start and end at any node as long as they go downwards from parent to child. So this point is to be noted carefully. Look, we don't only have to start from the root node. Fine, we could start from any node, but as if we start from 2, this becomes a parent node, right? And you go further downwards, not upwards. You have to go just downwards or the childs of that particular node. Fine, and you return the total number of such paths that sums up to the target sum. Fine. The question is pretty easy. I hope you understood. Let me clear this up. So in short, we have to find a path, find a path. Path sum should be equal to the target sum given, fine, and we have to find its total count, fine. So basically, count of the total paths which equal to the target sum. That's all. The constraint of the problems are the number of nodes in the tree is from 0 to 1000, and the node value could be from negative 10 to the power 9 to positive 10 to the power 9. And target sum value also could be from negative 1000 to positive 1000. So I hope you understood the problem explanation and the constraints given. Now let's move to the next slide. Let's understand the input output of the problem. So let's take this tree itself. Okay. So let me draw this tree. Okay. So this is our given tree, right? And our target sum is here 8. Fine. So where we can find 8, right? So if you take 5 as the root node or the parent node and we start from 5, then we can see that 5 plus 3 becomes one of the path. If you go from 5 to 3, you could get one path. 5 to 3, you are going downwards, okay? And sum is 8, right? Great. Then you could see if you take 5 again, 5 to 1, this complete path from 5 to 1 also sums up to a value of 8, right? 5, 2, then 1, right? Great. After that, if you take 3 as the parent node and you go from 3 minus 3 to 11, you could get another path, fine, minus 3 to 11. So in this complete tree, you could see that there are total 1, 2, and 3 paths whose sum is equals to 8, right? And which is basically equal to the target sum given, fine. So this is what our input output explanation was. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem, fine. Let's start by understanding the goal. So you're given a root of a binary tree. Fine. Let this be the root of a binary tree or the binary tree given to you. So the task is to count the total number of paths in the tree where the sum of the node values along the path equals the target sum. So you know the meaning of path sum as I explained earlier, right? So suppose this is a one path, okay, its sum is 2 and it is equals to the target sum. Fine. So this is one of the path. So the count will increase. Fine. So this way you have to find multiple paths which target sum or whose sum is equal to the target, right? And you have to take their counts. Now, one thing to be note is that you have to always move downwards, right? From parent to child in downward direction only. You cannot go to the upward direction. For example, if you're standing here, you're taking this as a parent node, you're not allowed to go above, right? You're going to allowed to go below only, right? That's the thing. And this is different from typical root leaf problems. How? What usually happens is that the tree is given to you this way, right? And they ask you to just find the path or the path sum or whatever from the root to the leaf. Fine. But here it is not like that. It is here you could consider any any of the the node as the parent. Suppose you consider this as the parent for your calculation. So the path will start from this node to the below child nodes, right? That's the thing. That is a catch here. Okay. So what could be a brute force solution? A brute force approach would consider each node as a starting node or starting point and explore all downward paths, checking if they add up to the target sum or not. Right? Let me make this clear to you by giving a small, just a kind of an example. Let's take example as let's take as this 10. Let's take this as the tree. Fine. So what I'm trying to say in the brute force is that, for example, you will come here and you will say that, okay, I will take 10 as my parent node. Fine. So in one iteration, you took 10 as the parent node. Then you said that I will iterate the other or leftover child nodes and I will try to find a path whose sum is equal to the target sum. Fine. So what you do is standing here, then you went below. Then what is the path? 10 plus 5, right? It's 15. So it's not what we need, right? When you move more below, it's 5 plus 10, 10 plus 5 plus 3. This is one path, right? And again you went below, so it's again 3. So if you can see in the complete path from 10 to 3, you got 10, 10 plus 5, 15, 15 plus 3, 18, 18 plus 3, 21, right? So none of the path gave you the sum equal to the target sum, and let the target sum be 8 here. Fine, no one gave you this solution from here, right? So what you did, okay, that's the thing. Now for this complete tree, you iterated the complete subtree, I will say, okay, or the child nodes, and you didn't got any of the solution, right? Then what you do, you thought that I will take 5 as my parent node. This is my parent node now. Now, as if you have taken 5 as a parent node, you cannot go above, right? You cannot go up. You have to just go downwards. So you are just left with this tree. Fine. Okay. So what you do, 5 is here. Then you went below to the next child. It is 3, right? So you check the sum. It is 8, right? So what happens? Our count becomes 1. Okay. Then you went more below to the child. Okay. Got another 3. Now the sum is 8 plus 3, 11, right? So it is not feasible, right? So what you do, you just go back. You come back to here. Then you try this path. The path is 5 plus 3 minus 2, right? Which basically gives you 6. So it is also not an efficient solution or the target solution, right? So you went back, then you tried coming to this path, right? So what is the path here? It is 5, then you went below to 2, then you went below to 1, right? So it's totally 8. So you got another path here. So one path was this, another path comes out to be this one. Great. So you got two paths. Now you thought that I will take minus 3 as my parent node and I will go downwards, right? So the path will be, let me write it here, minus 3. Then you went below, it's 11, right? So sum comes out to be 8. Okay, so you got another path. So the count become 3. So this is the way you can do the calculation of path using the brute force solution. But the issue is here, if you could see or if you observe, for each node, let me write it down. So for each node, what we will do here, we'll check for each node, you traverse the tree, subtree, right? So just keep in mind, for example, if you are traversing for each node the complete leftover tree, so for that, for each node traversal you need O of n complexity, right? Great. Now, for 5, suppose you came here and you thought of traversing the complete leftover subtree, right? It will take another O of n solution or time complexity, right? And because of which the total time complexity comes out to be O of n square because you're calling the tree or you're traversing the tree twice. For each node, you're traversing the tree twice. First for each node, second for that particular node, the leftover subtree, right? So that is why this solution is not so efficient to consider. Now let's look at the efficient solution, what it could be. If you could use a running sum and some data structure to remember how often certain sum occurred along the path. We could talk of like prefix sum concept here, right? Running sum is the keywords you can see, right? So let's look at the efficient solution, how we can do this in O of n solution itself, time complexity. Now let's try to visualize the process, fine, of the efficient solution O of n, how we gonna use the prefix sum here. So before going the solution, I will just bring you to the part that we will be using concept of prefix here and hashing. Okay, this is the two concept which we will be using. Fine, great. Now imagine we are at a node with value 5 and the total sum from the root to the node is 15. Okay, suppose there is a node here. I'm drawing the half of the tree and this is value 5 and this total sum comes out to be 15. Fine. If the target is 8, we check if there is a previous prefix sum of 15 minus 10. 15 is the total sum, 10 is the target, and it equals to 5, right? So we will check if there was any previously 5 value present in our path, and if it was present, that means that the target sum 10 there was a target sum 10 or a summation of 10 in the path from the particular node to a parent node to the particular node. Fine. So to clear this thing, let me take another proper example and make it understandable to you. So now let's try to solve this example so that you could understand the concept which we are trying to understand. Basically, this is not a concept. This thing comes from a question named subarray sum equals k. This complete thing is a solution to that particular question which we are going to implement in our binary tree, right? So I'm trying to explain you that particular question here, right? I have already drawn out the structure. Now let me make you understand what particular thing means. So this is the array. This is the target, right? Now here, map of 0 equals to 1. So since we know this concept uses uh, prefix, I have already mentioned you, prefix and hashing, right? In hashing in the Python, we are using here a dictionary. Okay. Now, if you could see, I have created a dictionary here, and here I have written it as map. So what map of 0 equals to 1 means? This means that we have seen we have seen one sum of 0 so far. Basically, this is the path. Here you find 0, then you're moving ahead. So in this complete path, you have already found only found sum which equals to 0 one time. Fine. Till here, particular till here. Say for example, right? If after that again you get a 0, so the sum will be not one time, it will be two times till here. Right? This is what this particular thing tries to tell us. Fine. Okay, this is the sum, current sum. This takes the difference. Fine. And what is this meaning of basically difference is that what sum we need before now to make the current subarray sum equals to k. Fine. This is what this particular difference value means. Fine. And this is the thing. Now we will move ahead, and as we proceed, you will automatically get what we are trying to do here. Okay, let's start. So one first index is one, sum is one, right? And one minus four gives me minus three, right? And it is not present in our map. Fine. So our sum is one, so we store sum here one. We take the count as one. Great. We move ahead. Now we are in two. So 1 plus 2 gives me what? It gives me 3, right? And 3 minus 4 is what? 3 minus 4 is minus 1. Since minus 1 is not present in our map, so we'll skip and we'll just store 3 in our map. We count as 1. Now we will move ahead. Now we are in 3. Now our sum is 6. Right? Great. Now 6 minus 4 gives us what? Gives us 2. Now we will check whether do we have 2 in our map. No, we don't have, right? So we just store 6 with it count as 1. Okay, we move ahead. Now we got minus 1. Okay, so 6 minus 1, 6 plus minus 1, it will be 5. And 5 minus 4 is what? 5 minus 4 is how much? It is 1, right? We check, do we have 1 in our map? We can see, yes, we do have 1 in our map. So what happens is that our count becomes 1. So we add the count here, correct? And now since sum is 5, we will put 5 here and we will increment its count to 1. Now you might be thinking that okay, how it is 1, right? But if you can observe here, we were standing in this index, right? Till this index, how many sub arrays are there whose sum is equals to 4? You could see that 2 plus 3 and minus 1 gives us 4. Is there any other sub array till here, till this index? You could see 1 plus 2, 3 plus 3, 6 minus 5. No, it is not there. 3 minus 1, it's 2. It is also not there, right? So we only have one sub array. So this difference in easy words, this difference tells us that up till this particular index, how many sub arrays are there whose sum is equals to 4. Fine. And how do we find out? We take out the difference from the target, and that difference is said to be that how many sum we need before now or before particular index to make the current sum equals to k. Fine. We look it into the map. If it is present here, that means that okay, we have it. And the count here says that how many times that particular sum has encountered. So we move ahead. We're in this. So this becomes 6 again. And we subtract 6 with 4, so we get 2. Since 2 is not in our map, but 6 was already there, right? So 6 count becomes 2. We move ahead. We are in here. Now 6 plus 2, it is 8. Then 8 minus 4 is 4, right? And we look into the map, there is no 4, right? So what we do, we put 8 here, we count as 1. We move ahead. It's minus 2. Minus 2 with addition with 8 gives me 6. And 6 minus 4 gives me 2. Correct? Then we look into the map. Do we have 2? No, we don't have 2 present here, right? So we just skip it, and since our current sum was 6, so we increase it to 3. Now we move ahead. Now it is 3. 6 plus 3 gives me 9. And 9 minus 4 is how much? It's 5, correct? We look into the map. Do we have it? Okay, we have it. And its count is 1. So what we do? We increment our count to 1 and uh, we put 9 here and we make it 1. So it says that now our count is 2, sorry, not 1, till here. Then if you could check that 1 was 2, 3 minus 1. Okay. Another sum if you could see here is what? If you have taken 1, 2, 1 or till 3, right? 1, 2 minus 2. If you could check this sum array, 2 minus 2, 3 and 1, which is basically 1, 2 minus 2, 3. We cancel this out, you get 4, correct? Till here, there are only 2. Then you move ahead, you have 10 now. And 10 minus 4, it's 6, right? Now we look that whether we have 6 in our map or not. Okay, we have. So we directly add it to our count. So our count becomes 5, right? Now, what are the other 3 sub-arrays, right? If you could see here, 2, 3 minus 1. You could take this 2, 3 minus 1 is taken. 1, 2 minus 2, 3 is taken. Another is 1, 2, 1. This one, 1, this 2, and that one. So how much is 1, 2, 3 plus 1, 4, right? Another subarray is, let me write it here. 1, 2, 1, and we clear this up. 1, 2, 1 from index 0 to 3. Another 1, 2, 1 is there, which is from 8 to 9. Fine. And 3, comma 1 is there from index 7 to 8. Fine. This one. And this index, if you are not able to look it out, it is from 0. It is from 1 to 3. And this one is from 0 to 3. Correct? And after that, you come here. 10 plus 2 becomes 12, right? And 12 minus 4 is how much? It is 8, right? So you look into the map, you find 8 is there, so you increase the count by 1. So it becomes 6, and therefore our answer comes out to be 6. So there are total 6 subarrays. So this is the complete concept of finding the subarray sum. Okay. Now this exact concept we will be applying in our process here. Suppose if this is a tree, we will do the same thing. We will take this, we will add up to the sum, correct? So instead of tracking every path, you could say if such a sum exists, it means that node between the prefix and the current node from a path that adds to a target sum. So we will do the same thing here, and if we get that particular thing in our map, we will increase the count as we did earlier in our array example. And this way, we can instantly know how many valid paths and at the current node in constant time. Right? Now let's move ahead. Now, how we can simulate this complete process? We could use DFS traversal, which is the common traversal of the binary tree. And as we move down, we just create a random tree here. As we move down the tree, we maintain a running sum. We will have a current sum similar to that example. Okay. For each node, we will check the current sum minus the target sum difference. If it exists in the prefix sum map, if it exists in the map which we created already. If yes, we increase the frequency. If you could see, this is exactly the same thing which we did here. We check for the sum, we check for the difference, we check if it exists in the map. If it exists, we add up the sum here, right? Exactly, we will do that. We increment the count of the frequency and update the prefix sum, same thing. And after visiting both the children, now here is one catch. Suppose if you have traversed this path, right? Now, since array is a linear data structure, right? 1D array, and you are moving only in one direction. There is nothing to be coming back, right? But in tree, if you come here, then you might have to go back and come in this direction, right? So when you move back, you have to remove this sum or this sum value from the prefix map. Fine. Otherwise, this complete map will be calculated as some vague path. So since this is a different path, we will calculate this, and when we come back, this will be deducted. This path sum will be deducted, and this will become a new path. Fine. This is the thing which we will be doing. It's pretty easy. Now, what we figured out? We figured out that by using prefix sum and hash map and DFS traversal, we can efficiently count all the valid paths with the required sum in O of n time. The prefix sum strategy avoids redundant Cauchy computation of n square solution which we were doing already. And this we optimize the solution by converting the problem into a variant of subarray sum using prefix sum. This is a problem number we want to solve 560 in Leetcode. Fine. This is the particular question, and we used basically this concept and to adapt to the tree structure. That's the thing. I hope you understood the intuition. Now let's move to the approach. Now, since you got the intuition of the problem, let's look into the approach and how we're going to solve it. Fine. It's simple. We will in path sum, the given function, it is the given function. Fine. We will initialize a dictionary named prefix sum to store the values, right? If you remember, we stored 0 with count as 1. This handles the case where a path from root to directly equals to target sum. Now we start the recursive DFS from, and we create this helper function where we will pass the root, the current sum, the target sum, and the prefix sum, which is basically the dictionary. Fine. And why we do this? Prefix sum of 0 allows paths that start from the root and some target sum to be counted correctly from the beginning. So one thing is that why we store 0, right? We stored 0 before because there might be a case where sum is 8 and difference is also 8 and it becomes 0, right? So there might be a path from 0 to somewhere where we get a sum 8. That is why for our safe side or the target sum to be calculated correctly, we store 0 beforehand. Fine. Now we define the recursive helper function to count valid paths. So we create a helper function, find path, which has the root, of course, the current sum, target sum, and the prefix sum. These are the four things which are the mainly required, right? Now, if the root is none, we return immediately. This is the base case. So suppose if there is no root, suppose you are standing here, if you're in a leaf node and you check if there is left or node or not, right? If it is not, we will return, right? Similarly, if the tree is only not given, then also you have to return. So that becomes the base case. Otherwise, we add the current node values to the current sum. Since we are going down, we keep on adding the sum and we keep on computing the difference on the go. This whole thing is going on the go. Suppose this is the tree, right? Just assume it to be a one array going this way. Forget about the other nodes. Fine. So just suppose this is one array and you're going downwards and you're computing the same thing which we learned earlier. If this difference has been seen before in the prefix sum, it means there are one or more subpaths ending at the node. So what we do, we check in the prefix sum, right? Like if it is there, we take the total, add that count of frequency to our total sum. Now we increase the frequency of the current prefix sum in the hash map. Like map, if you remember, there was a sum, we increase by one, right? Recursively call the find path sum on the left and right children, passing the updated current sum. Now, after the process of both trees, suppose we calculated this path also and this path also, right? Now, let me clear and show you again. The same thing again. What does this last line is trying to say is that if you are in this path, right, you calculate it completely. This is of course a different path, right? And we cannot include the sum or the prefix sum value from the map of this particular node in this path, right? So when we go back, we have to remove this prefix sum from our map, okay? So that this is removed and we can get a correct answer of this particular path. Okay, this is what is saying here. Now, after doing all the like traversing and finding the prefix sum and stuff, we at the end just return the total sum as a final result. That's all. The approach was exactly what we discussed in our intuition and as well as in our example or the understanding of the survey sum of value k, right? I hope you understood the approach. Now let's move to the next slide. The code is the exact copy of the approach we discussed. It is exactly the same. Let's understand it line by line. It starts from here, right? If you can see, we have created a dictionary and we have stored zeroth value with count as 1. You already know why. Okay. Now we call this function with these values. This part is done. Now this is the main function where if it is not root, this is the base case, we return. Otherwise, we keep on adding the current sum. We take the difference. We check if it is present in our dictionary or not. If it is not present, we just return 0. If it is present, we take out the difference value, okay, and we add it to our total sum. And in prefix sum map or dictionary, we store the count of current sum. Fine. This is the same thing which we were doing in our example understanding, right? Then we call for the left subtree, and the right, then after that right subtree. Now this is the main catch here. After doing this complete traversal, when we go back, we have to remove that particular current sum from our prefix sum so that it does not collide with the new path, right? That's it. And after that, this is completely done. We return the total sum from here. Now, the total time complexity comes out to be O of n here in this case because we are just traversing the complete uh, tree only one time. Fine. And space complexity is O of n because we are using a dictionary and we are storing at least or at most O of n value to it. That's why. I hope you understood the code explanation. Now let's move to the next slide. Now, since you have the understanding of the code, let's look at the dry run of the example. Fine. Let me draw the tree for this particular example here. Okay, so this is the tree I have created. Okay, uh, let me bring up the code also here. Okay, so I have drawn the tree also and I have brought the code also that you could understand it much clearly. So this is the tree. Okay, I hope you have the understanding of the sub array sum equals to k. which I already explained you in the intuition part. Okay, now let's go try run. So it all starts with the dictionary here. Let me create a dictionary. Now prefix of this is a prefix sum 0 equals to 1. Fine. Now I have passed your root 0 sum. Let me create a sum here and prefix sum, which is this dictionary, and that's all. Okay. Now if root is not on, okay, we are standing here. Let me take another color. Okay, so we are standing here. Fine. In current sum, we take the current sum value, which is root value, which is 5. Okay. Our target sum here is 20. Please keep that in mind. Okay, fine. 5. Then we moved. This is done. Then we take the difference, which is what? 5 current sum minus target sum. It comes out to be some large negative value. Of course, it is not presented here. So it will be, I think, 17, negative 17. It is not in the map, so we ignore it. And what we do, since it is not there, so our total sum remains 0. Okay, then we move ahead. Then in current sum, we store it in the map. Fine. Then we come here. Now it's 5 plus 4, it's 9, right? Now 9 minus 22. I guess it is a bigger number again. Minus 13. And again, minus 13 is not in the map. So we ignore that part and we keep the sum in our map and move ahead, right? This is the part where we are storing in the map, the current sum. Fine. And we go to the left side. This is the left call. This below is the right call. Fine. Please look at the code. Then we are in here. Then 9 plus 11 gives me 20. And if I do 20 minus 22, it's minus 2, and minus 2 is not in the map, so we ignore it and we just store the current sum into the map. Give its count as 1. We move ahead. Now it is 7. So the sum becomes 27. And now 27 minus 22, how much it is? Gives me 5. Correct? So we look into the map. Okay, we can see there is 5 here, where the count is 1. So our count becomes 1. Fine. And we store this 27 into our map. Fine. Let me clean this up now. This part is done. Very good. Now, if you are wondering how, so if you could see here, 5 plus 4 plus 11 plus 7. 5, 4, 11, and 7 gives me 27. This is done. Fine. Now, if you could see, we are cancelling this part because this is one path, right? And this will be a different path. We cannot include this value in it, right? That's why we remove it from our map. Current sum. So we move back. Okay. So we move back and we remove this 27. The current sum is 27, right? So we remove it from our queue. Minus 1. Okay. And this sum is 27 now. Fine. Now for this iteration, the sum is 20. Now please keep that in mind. Since still here it was 27, right? And when we went back, we removed it from our queue, correct? Sorry, map. And when we move back or the recursive call goes to the parent call, the sum reduces automatically. It is done by the recursion, so you don't have to worry about it, right? So what happens now? 11 is there, right? Which is sum is 20. Then 2 is added. So it becomes 22, correct? And 22 minus 22 gives me 0, right? And we look into the map, and we could see that, okay, we have a map value 0, correct? We look it in here. So we increase the count to 2. And we store this 22 into our map with 1. Great. When we move ahead, there is nothing, right? And we have to go back again, right? Now, since from 2 to 5, we have to go back completely, right? So all the values or all the current sum will get removed from here, from the map. 22 will get removed, 20 will get removed, then 5 plus 4, 9 will also get removed. And the sum will become again, total count will be 2 and sum will be 5 again. This is done by recursion. Please don't worry about that. Fine. We just have to worry about the map. Now we go and look for this right side because this iteration is done. Now we look for the right path. So it's 5 plus 8. How much? 8. 5 plus 8 is 13, right? So we store 13 and 13 minus 22 gives us minus 10. And since minus 9 is not in the map, so what we do, we just store 13 in the map and we keep the counter on. Then we go to the left. Now 13 plus 13 is how much? 26. And 26 minus 22 gives us 4. And it is also not in our map. So we just store 26 into our map and we move ahead. Correct? Now we could see that this is ended, so we go back. So this 26 is removed from our map and from here also. Fine. Now we go for this path. 13 plus 4, how much? 17, right? And 17 minus 22 gives us negative 5. Since negative 5 is not present in our map, so we ignore it and we just store 17 into our map. And we come to the left side. Now 17 plus 5, how much it is? This 22. We are in this path now. We are standing in 5 now. So it is total sum is 22. And again 22 minus 22, it is 0. Correct? And in the map, we could see we have 0, right? And its count is 1. So it increases by 1. So it becomes 3. And we store 22 into our map. Now, this iteration is done for this leaf node. So we go back. Fine. As we go back, we will remove this from our map and also our sum will reduce. So our sum becomes 17 again. Now in this 17, we will come to this path. It becomes 18. Correct? And 18 minus 22 is how much? 4. And we look into the map, there is no 4, right? So we just ignore it and we go back. So this and we go back again, and this sum completely gets reduced to 0 again, right? And everything from the maps gets cleared out as we move ahead or move above to the root node again. And at the end, we return 3. If you could see, 3 is our all the solution to this particular problem. So I hope you understood the dry run. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the prefix concept, uh, then the hash map if you don't know anything about hash map or dictionary, okay, and then the approach and then the code. After that, do a dry run by yourself on 2 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since we are familiar with the problem and the solution, let's move to the lead code and code the solution. Let's code it out. So first I will declare this into inside the init method. Fine. Self dot total sum equals to 0. Fine. This will result in our total count. Or instead of total sum, we could just make it total count also. Fine. Same thing. I will create a prefix sum hash map using dictionary. Default with integer and prefix sum of 0 is equals to 1. Self dot find path sum. We will pass how much? We will pass root, current sum, target sum, prefix sum to it. Fine. And we will return self dot total count. Fine. Now let's define find path sum function. It has the root, current sum, target sum, and prefix sum. If root is not there, if not root, we come back. Right. Otherwise, we store the current. Um, this spelling is wrong. Okay, I will store the current sum root value. And again, if you remember, we take the difference for every time, right? Current sum minus the target sum from the target sum, then self dot total count. Now please pay attention here. We add the total count from the prefix sum dictionary. We check that we try to get that whether we have the difference or not. If we don't have, just return 0. And either of the condition, we will just add the current sum into our dictionary. Fine. Current sum is added here with increment of 1. Then we will call for the left subtree, find path sum root dot left current sum target sum prefix sum self dot again find path sum to the right current sum target sum prefix sum prefix sum. And when we go back, if you remember, we were removing that particular thing from our map, right? So this is the line number 28, where we remove the uh, current sum value from the map. Fine. Now I will just run and check the base test cases. Okay. Now finally submit the solution. Okay, we successfully submitted our solution. Now code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.